Hi Math 30-1s, just going to continue on today with applications of exponential and log functions. What we're going to work on primarily today are some word problems, okay, involving the exponential function, which in general, okay, is this equation right here. So what we're going to have to work on and focus on today, okay, is determining the values for a and b in those equations. And later on in the lesson, you'll see determining the value of x as well, the exponent. Now, what's important here is it's as we start and read through the equations, okay, right here, where it says where a is bigger than 0. So remember, when they're telling you something is bigger than 0, again, they're just referring to that value is positive. Okay, they move on to b, so we know a is positive. They say when b is bigger than 1, the function represents a growth function. Okay, so if you were to graph that, okay, we know a growth function goes up and to the right. When b is between 0 and 1, okay, so it's a fraction between 0 and 1, okay, we're going to have a decay function, which is going to be something that goes down in this direction. Okay, so those are the two shapes of the graphs that we are going to be working on. Now, a little extra here that'll make the lesson easier later on is when b is bigger than 1, so the growth function, what we do is we take a percentage or a value and we add it to the number 1 because the number 1 represents 100%. When we are dealing with a decay function, the percentage or the value we are going to subtract from the number 1, okay, or from 100%. So that's how we determine that b value. If things are increasing, it's 1 plus a value. If it is decreasing, it's 1 minus a value. And again, I will refer to that several times in the lesson, but just some insight as to where we're going with the lesson today. So it says writing an equation using y equals a b to the exponent of x. There are many applications of exponential functions in real life. In some cases, that exponential function is in disguised form, and that was basically what we saw yesterday, okay, which was our compound interest formula, which is right here, okay, a p 1 plus I to the exponent of n. Remember that in that formula, a is like your variable y, the p is like our variable a, the 1 plus I is the b, and the n is the x. Okay, so it does take on that exponential equation and function. We can use variations of that formula to solve problems involving what we call population growth, okay, growth of bacteria, radioactive decay. Okay, so growth and decay are two words that we're going to be using over and over again in this lesson and till the end of the chapter. So first question, we just jump into questions here. It says in 2012, the university population of a country was 160,000 and was increasing at a rate of 4.5% annually. Okay, so again, what's important there is we are increasing at 4.5%. So I will take a look at what that means here in a second as we state the values for a and b in part 1 of the question. Okay, so it says if the function representing the population is exponential, y equals a b to the exponent of x, what are the values of a and b? Well, a is always our starting or our initial amount. So in this case, that's going to be 160,000. Now the value of b, like I mentioned at the top of the lesson at the beginning, is either determined by going 1 plus or 100% plus, or 1 minus or 100% minus, depending on whether we're increasing or decreasing. Well, in this question, as I've underlined, we are increasing. So I'm going to be adding 4.5% to 100%. So as a decimal, this will be 1.045. I've added 4.5% to 100%. Okay, so I have 1.045. That's my value of b. Part B of the question reads like this. Write an equation to represent the university population, P, of the country as a function of the number of years, N, since 2012. So I have to use the variables that they have provided for me in this question. So the population, P, will be equal to the A value, or my starting amount, 160,000, my B value, or the rate at which the population is growing, and then instead of to the exponent of x, it's to the exponent of n in this question. So again, if you were to go and take a look at this and you graphed it, okay, the reason that those variables are important are because now I know that on the y-axis, I would have the variable p, and on the x-axis, I would have the variable n. Okay, so again, we know that if we take a look at a graph or try and graph this to answer any questions, we know what the dependent and the independent variables are. Okay, in part C, it says now determine the population in the year 2015. Well, if we're talking about 2015, okay, we started this question in 2012, so that means the value of n is 3. Okay, 3 years have passed from 212 to 215. So when I go into the equation algebraically, I can simply go p is equal to 160,000, 1.045, and now to the exponent of 3. Okay, and again, just to reiterate what we learned yesterday, I want to first go 1.045 to the exponent of 3 first, and then multiply that value by 160,000. So when I do that, the population ends up being 182,587. Okay, so there's our population. Now, in part D, it says if the population continues to grow at this rate, determine the number of years. So this time they're looking for the n value. They want the number of years to the nearest year for the population to double from 2012. Okay, so what I'm going to do is just write out the equation that I'm starting with. So p is equal to 160,000. 1.045 to the exponent of n. Now, I know from the question they want the population to double, so that means my final population will therefore be 320,000, okay, double the 160,000, okay? And just like yesterday, what we do to solve for that exponent, which is our variable, is first I divide both sides of the equation by the a value, the 160,000. So when I go 320,000 divided by 160,000, that is simply going to be 2. So I now have 2 is equal to 1.045 to the exponent of n. So now we can use our laws of logarithms to solve for n. So I go log 2 is equal to n, and then the logarithm of 1.045. And therefore now I just divide both sides of the equation by the logarithm of 1.045, okay? And that will isolate n, which is what I'm after. So on my calculator, when I do that calculation, okay, I end up with a value of n that is 15.747, etc. Again, don't round quite yet. I go back to the question and they want it to the nearest year. So in this case, I use my rounding. I'm at 15.7. So to the nearest year, that will be 16 years. Okay, that's my value of n. Okay, so again, with these questions, once you have the equation, they're only going to ask you one of two things. They're going to give you the x value and they want the y, or they're going to give you the y and ask you to solve for the x. Okay, that's all that they're going to do in these questions. So just be sure that, you know, calculations like we did in C and D, that you are comfortable doing those. All right, next page. So on the next page, it says the number of fish in a lake is, and here's the important part, decreasing by 5% each year. So going down by 5%. Part A says if the number of fish present is an exponential function of time, state the base of the exponential function. So the base of your exponential function is the value of b. Okay, it's b in your exponential equation. So b is going to be 0.95. Now, how do I get that? Well, decimal 95 is 95%, isn't it? So what I did is I started with 100% and I subtracted the 5%. Okay, so that ends up being 95%. Or if you think about it in terms of decimals, 1 is 100% minus 0.05. There's your 5%. So 0.95 as a decimal. So either way that you want to think of it, okay, whatever makes more sense to you is great, but either way you have to end up with that b value being 0.95. Each year that passes, I have 95% of what I had the previous year. Now, in B, it says write an equation to represent the number of fish present after t years. Use n naught or n subscript 0 to represent the initial population and n of t to represent the final population. So your equation looks like this. Here's n of t, so that's your y value. Okay, will equal the initial population times the growth rate of 95% and to the exponent of t. That's the variable we're using in the question. So again, it's exponential, right? Y is equal to a b to the exponent of x. Okay, so it still follows that same general formula. So C and D now, they're just going to ask us questions based on what we've done so far and the write-up and information they've given me in the question. So in C, it says, if there were 2,500 fish present in June of 2012, how many would you expect to be present in June of 2017? So that means I want to know from 2012 to 2017. So the time that has passed in this question, T would be equal to 5 years. Okay, so the number of fish present after 5 years would be equal to, I'm going to start with 2,500, the growth rate of 95%, and then to the exponent of 5. Okay, so the number of fish present after 5 years will be equal to, and again we do 0.95 to the exponent of 5 first, and then I multiply that value by 2,500, so that gives me 1,934 fish. Okay, as a decimal, it's 0.45, but we have to round logically here. If I don't have enough to make the next fish, I don't have that next fish. So 1,934. Now in D, like I mentioned before, what they're going to do now is most likely give me the y value and ask me to solve for the x, which in this case is the value of t. And that's what they see here. See how many years to the nearest tenth, so this time to 1 decimal place, would it take for the fish population to reduce to half of the number of fish basically in June 2012. So again, I'll just set up my general equation. Okay, never a bad idea just to start at the beginning. So you start with your 2,500 fish, the growth rate of 95%, okay, and t is time. Now, they want the population to be half. So half of 2,500 is 1,250. So there is half of the population. Okay, and I'm still focused on solving for t. So again, divide both sides of the equation by the a value, which in this case is 2,500, and you'll end up with 1/2, which is 0.5. Okay, so now this is the equation I'm left to solve, and we follow similar steps. So I'm not going to be able to create powers with a common base, so I take the common log of both sides, like so, bring that exponent down in front of the log of 0.95, and then divide both sides of the equation by the logarithm of 0.95. Okay, and there's an expression for the value of t. Now I actually do that equation, and to the nearest tenth, okay, so this calculation when you do it will end up being 13.51, etc. Okay, so to the nearest tenth, 1 decimal place, it'll be 13.5 years. Okay, and there are our answers. Okay, moving on. Now the next question, again, if you remember from other lessons that we talked about, anything where we deal with base e, okay, or natural logarithms, okay, we are not responsible for. So this question, again, we are able to omit. Okay, we do not have to deal with these questions. Okay, so that's good news. We're going to move on to the next page. Okay. So on the next page, some very important terminology, okay? So on the next page, what you see are things that are what we call half-life, doubling time, etc. Now, when you see those key phrases, half-life, doubling time, they're automatically telling you what the b value is, okay? So they're telling you what the b value is going to be in your equation. So half-life, for example, your b value would be 1/2. Doubling time, which means multiplying by 2, your b value is going to be 2. All right, so pay really close attention to those key phrases. They're automatically telling you what the b value or the growth rate in your question is. The other thing that is going to change with these questions when you see those key phrases is the exponent. The exponent will be what we call a rational number now. So your exponent, okay, will now be rational, which means it's going to be one value over another. So we know that a rational number is written like this, a over b. So those are the two changes to the question when we see key phrases like half-life, doubling time, tripling time, etc. Okay, so what happens is I've explained pretty much what we need to look at here in half-life. Okay, and you can see here in half-life, okay, there is the 1/2, and there is the exponent, okay, which is a rational number. When I move down to doubling time, okay, like I had said, here is the b value of 2 to represent doubling, okay, and here is the exponent, which ends up being a rational number, okay. So that's all that's really being taken a look at on that page, okay. They're asking me to develop formulas. I'm not going to develop the formulas. You're not going to be asked to do that. We're just going to be asked to use them in the context of a problem. So we're going to move to the next page, and I'm going to describe all the variables here and what they mean and help you highlight and make notes of the important stuff. So on the next page, they have the formulas for, like I said, doubling time, tripling time, half-life, etc. Those are the key phrases that indicate to you that I'm going to have a very specific b value and your exponent is going to be a rational number. Okay, so that's all that they're working through here in these questions. Okay, again, they tell you that a naught or a subscript 0 is your initial time, a is your final amount, c is basically your b value. Okay, so 2 for doubling, 3 for tripling, half for half-life. Now, these two are the new ones, T and P. Those are the variables that you can see up here in the top right corner are your variables that make up the exponent. T is time, so the length of time that has passed in the question, and P is the period of time for doubling, tripling, halving. Okay, so what the period means is how long does it take for the thing to double or halve. And again, I'm not just going to leave you with that explanation and say good luck. I will mention that several times between now and the end of this lesson, so hopefully that's clear. So a lot of times those values of T and P are the things that give students trouble. So we just need to make sure we're really clear on what those two are being defined as in the question, and then these are pretty straightforward. Okay, you'll find them easy. So let's read the first question here, and I'll help you pull out the important information. So it says, a patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. So that's going to be our starting amount, okay? So they're sick, they have a sample taken, boom, 387 cells, that's what we're starting with. 24 hours later. Now, that's time. That's how much time has passed, okay? So that's going to be our variable t in the question, which is in the exponent. Later, the sample was recounted, and now there was 8,012 cells. Well, that's the final amount of cells. Okay, so that's going to be the value that goes on the left-hand side of the equation. Find the doubling period. So they want you to find the period. That's going to be the p-value. But they've also said it is doubling, so now you know what the b value is. It's 2. So what I do is I go into my equation, and I write it like this. So 8,012, that's going to be the amount that I end up with. My starting amount is 387. My b value is 2 because I have a doubling period. Okay, so that's how I know automatically that that value is 2. And I'm just going to erase that arrow so that I can write in my exponents. Now the exponent, remember, is going to be t over p. Now remember in the question I said I know what the time is. It's 24 hours. So when I go into my exponent here, I will be replacing time, 24 hours, not p. P is the period, how often or how long it takes this bacteria in this question to double, and that's what we're after here. So same steps. First thing I'm going to do is divide both sides of the equation by 387. So I go 8,012 divide by 387. That gives me a value of 20.702. Okay, and again, I write etc. here. I do not round that value. Okay, I leave it in my calculator. I'm going to be using that whole value until the very end of the question. Now, from here, you have to stay true to the process that we've used in the last couple lessons. What would I do next? Well, first I would take the common log of both sides of the equation, okay, like so, and bring that exponent down in front. So the exponent this time is just 24 over p. It's a rational number, and then log 2. Okay, again, I will now divide both sides of the question by the logarithm of 2. Okay, like so, and that leaves me on the right-hand side with 24 over p. So I'm going to do that calculation. Okay, I'm going to go the log of my answer here, divided by log of 2, and that gives me 4.371, okay, etc. So again, I do not round that value, and that is equal to 24 over p. Now what I have to do is get to that value of p, which is in the denominator. So when we Cross multiply and divide, what ends up happening is that those two values end up changing place, okay, in a two-step process, but P ends up equaling 24 divided by that 4.371, etc. So I'm just going to go 24 divided by that answer, and we get 5.5 to the nearest tenth. Okay, so P is 5.5, and that is hours. Okay, so what does that mean? That means the doubling time is 5.5 hours or 5.5 hours. So every 5.5 hours, that bacteria is doubling in amount. That's what you have just calculated, the length of time it takes for the bacteria to double. Okay, next question. In April 1986, the nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine 131. So that's just a type of iodine, radioactive iodine. It's not a value we're going to use in the question. If the half-life, okay, so there's the key phrase. What are they telling you there? Your B value is 1/2. So if the half-life of the radioactive iodine is 8.1 days, so here is the period. Okay, that's how long it takes the radioactive iodine to half. So every 8.1 days, you have half the amount you previously had. Determine the number of days. Okay, so how long? That's what they want. So this time they want time, the number of days, to the nearest day. Okay, so that's how we're going to round. It took for the radiation to reduce to 2% of the original level. Now, in this question, and again, I think we should put a star beside this one, okay, because it is really important. And the reason this one's so important is because if you notice, I didn't highlight any starting amount or any final amount. And they do that on purpose. Now, the reason they don't have to do that is because it really doesn't matter if I know that I'm reducing to 2% of the original amount, right? So for example, I could say that I started with 10 and I end up with, for example, outside the context of this question, let's say I end up with 5, right? Well, what would I do when I go and solve this question? I would go 5 divided by 10, okay, which ends up equaling 1/2. So I ended up with half the amount. So when I do that, all I really need to know is I don't need to know these two values. I need to know what happens when I take the final amount and I divide it by the initial amount. That's all that I need to know, the percentage, which they've given me, and that's 2%. So when I go to my question and I set up the equation, I can do this, and I'll show you. So there's the final amount, there's the initial amount. Okay, my B value is 1/2. Okay, I'll just write that as 0.5. You can use 1/2 if you prefer. And remember, my exponent is T over P. Now, in this question, okay, I know that they have given me the period. So this time, I know the period length of the halving, 8.1. Okay, so this is where the 2% comes from. Remember, in solving this equation, the first thing I would do is I would go A, and I would be dividing it by the initial amount. So A divided by the initial amount would equal 0.5, and then to the exponent of T over 8.1. Now, I don't know what the final amount and initial amount are, but I know that when I divide them, I get 2%. 2% as a decimal is 0.02. So 0.02 equals 0.5 to the exponent of T over 8.1. And now from here, okay, we keep going with our process. I take the log of both sides, the common logarithm of both sides, and bring the exponent down in front of the logarithm on the right-hand side of the equation, like so. Okay, I then, again, divide both sides of the equation by the log from the right-hand side, okay, which will leave me with T over 8.1. So I need to do this calculation of the log of 0.02 divided by the log of 0.5. So I get 5.6438, and again, etc. I do not use that value or round it yet. And then to isolate T, I'm going to multiply both sides of the equation by 8.1. So that will give me 45.7, etc. equals T. And remember, those are days. Now, they said to the nearest day, so 45.7 to the nearest day is 46. So 46 days is equal to the length of time in this question. Okay, so Couple things in this example, they don't give you a starting and a final amount, but they tell you the percentage that is left after you do that calculation of final amount divided by initial, 2%, so 0.02. So that's the first thing. And the other one is that's your first look at solving for the t or time in that exponent, okay, as opposed to the p-value. Okay, next page. So a couple similar questions left, and then that is it. And then we are done for this lesson. So here it reads that a radioactive isotope, okay, again, half-life, so there's your B value, of 7 years. So they're telling you what the half-life is. That's the period. So they've now told you the B value, and they have also told you the P. It says use the formula A is equal to A naught C to the exponent of T over P, with C equaling 1/2, which makes sense because that's your B value basically, to determine how much of the isotope must initially be present. So if they're looking for how much is initially present, that's this, right? What we started with, to decay to 60 grams in 14 years. So 60 grams will be your final amount, and 14 years, well, that will be your time. So when I go into the equation, I'll show you what we are solving for and what we are replacing with what, okay, based on the information they've given me. T over P. Now, the final amount they want to decay to 60. So they want that to be the final amount. They're looking for the initial amount. My C value is 1/2 or 0.5 if you prefer. The time they said in this question is 14, and the half-life is 7 years. So that's the period. So 14 over 2 or 7. Sorry, I did the calculation for you, didn't I? So this is 1/2 2. So I can carry on with this calculation. This will be 60 is equal to the initial. 1/2 squared is 1 over 4. Okay, to get rid of that 1 over 4 on the right-hand side of the equation, I multiply both sides of the equation by 4. So 60 times 4 is 240, and those are grams, okay? That is equal to the initial amount. Okay, so that's what we have. If we would have started with 240, 7 years, okay, to 60. Now it says write an equivalent formula, okay, with C equaling 2, which could be used to solve the problem. So they're just saying, I don't know why, they want me to use 2 instead of 1/2. So what I would do is the following. I would just have 60 is equal to the initial amount. Now they want me to use 2 here. So what I would have to do is instead of having 2 at the top, I'd have to go -2. Okay, because I've changed the B value from 1/2 to 2. Okay, it's going to give you the same answer in the end. I just made the exponent on the outside negative, which would move that value to the denominator when I do the calculation. So last part of this question reads like this. In this particular example, explain how the solution in A could be found without using a formula. Well, pretty straightforward, right? This is just using counting. Now this will work only for very few and very simple examples. That I know every 7 years, the basically the amount of the isotope is halving. So basically I'm going to go backwards, right? Instead of saying, okay, I finish at 60, I'm going to say, okay, I'm going to start with 60. And then I know that if I work backwards, okay, so this time frame will be 7 years, instead of it halving, it's going to double. Okay, I'm just going to do the opposite. So 7 years has passed, it doubles. Okay, then I'll do the same thing again. 7 more years have passed, it's going to double. And there you go, okay? Because if I take the 2 time frames, 7 years and 7 years, that's a total of 14 years that have passed, okay? And that's exactly what they asked for in the question, okay? It basically decays to 60 grams in 14 years, so I worked backwards. I started with 60, I doubled every 7 years, so 14 years have passed, and I end up at a final amount of 240, and that's it. Now that won't work for many questions. Obviously, part C here they can ask because it's a pretty straightforward, pretty simple question, and I only had to double the amount twice to get to the final answer, so it doesn't take too long. Okay, so hopefully that makes sense, you guys. Pretty similar to last day in terms of us working with the exponential function, y equals ab to the x. Just remember that b value, if we are increasing a population, like we saw early on in the lesson, it's 100% plus the increase. If we're decreasing, it's 100% minus the decrease. And then once we get into half-life, doubling, tripling, those types of things, You automatically know from the write-up of the question what your b value is, and your exponent is now t over p. It is now a rational number where t stands for time and p stands for period, how long it takes for the bacteria culture, whatever it is we're discussing, to double, triple, or half. All right, so as always, questions, send them to me. I'll get back to you with explanations and some helpful hints. Hope you guys are staying safe and healthy.